In this video, we're going to talk about graphing quadratic functions. So we have an example of a quadratic function here, x squared minus 6x plus 4. If we wanted to graph this quadratic function, if we have our sweet little calculators, we would go in and we would make a table, editing our function, putting in, oops, too many times, table, edit function, and we would go, let's clear out what's in there. We need x squared minus 6x plus 4. Doesn't matter where we start our table, we'll just have it fill in. And now we have a table that we can go ahead and graph with. So I'm going to just make the table over off, oops, to the side, so we can kind of see this. Okay, so we got our x and our y's. I'm going to go up and down, sort of try to figure out where we need to be in. All right, okay, so we see positive 4, and then we get 11 and 20. So we're starting to get off what we would actually want to graph. So let's start with that negative 1. So negative 1, we have 11. 0, we have 4. 1 is negative 1. 2 is negative 4. 3 is negative 5. 4. We have our negative 4. 5 is negative 1, 6 is 4. And here's where we can start seeing the symmetry of our quadratic function, right? We can see 2 and 4 both have the same output, 1 and 5 have the same output, 0 and 6 have the same output. This is what's letting us know 3, negative 5 is our vertex. Now, if we don't have the sweet table that we could use and then graph and just kind of visually see where our vertex, where all these other pieces are, what we might want to do is start by using the Vertex Shortcut. So if you're Isaac or someone who hasn't bought this sweet little 36X Pro calculator, what you would do to start is you would do the Vertex Shortcut. And remember, our Vertex Shortcut is x is equal to negative b over 2a. And then we just plug into this. We go, okay, negative b, well, b was equal to negative 6. So a negative 6 divided by 2a. Oh, well, I need to put a in there, right? A is 1. This is just 6 divided by 2, which is 3. This tells you where your vertex is. So if you're Isaac and you don't have the sweet table that you can just move around willy-nilly in, what you would do now is you'd go, okay, x, y, I want to start at 3. I know that's my vertex. And then you would just plug 3 into the equation. So you'd sit there and go, okay, well, 3 squared minus 6 times 3 plus 4, and you type that into your calculator, whatever the heck it was. You'd go, okay, 3 squared minus 6 times 3 plus 4 is a negative 5. Same thing we did, but with the table, but doing a little more work. And then you go, okay, well, let me try the next number, 4. 4 squared minus 6 times 4 plus 4. Again, we plug all that in, 4 squared minus 6 times 4 plus 4, we get our negative 4 out. And now what should happen, we should have that same symmetry. And so if you don't have the calculator, you should be able to leverage the symmetry so that you only ever have to do one side of the vertex. If you want to check that your vertex is right, which is probably a smart thing to do, you should at least check the other side before you start just using this. So we do a 2 squared minus 6 times 2 plus 4. And we'd verify, okay, this is negative 4. We did not, this is definitely the vertex. We feel very good. And now when I plug in 5, when I plug in 6, I know that whatever answer I get here is also going to be the answer on the left-hand side. So that's how you would do it or set it up if you have the, you don't have the sweet table in your calculator. So now that we've accomplished our table, both with and without our sweet calculators, we have to graph this, which is simply just putting down all these points on a graph. So we'll go ahead and say, all right, I can do this. Looks like I need to go all the way to 6 and negative 1, and I got to go all the way up 5, 6, 7, 8, 10, 11, and down to 5. And then I just put all those points on there. So negative 1 is at 11, 0 is at 4, 1 is at negative 1. Oops, I almost put that in the wrong place. 2 is at negative 4. 3 is at negative 5. And then we have those identical points coming back up the other side of our parabola. So we can go, whoop, we've got our parabola. All right, and so if we didn't recognize that this middle point here was the vertex based on that symmetry, we would at least be able to spot that our vertex was here and figure out that this was, oops, at 3, -5. So 3, -5. All right, so you guys know I'm not just going to ask you for the graph. I'm also going to ask you for some additional pieces. Actually, I want to keep that. I take it back. What we would want in addition to our graph and our table is that we would like to figure out our y-intercept. So our y-intercept, this one you can always just grab straight off the table. Y-intercept is when we set x equal to 0. You can also grab this off the graph. We can see when we cross the y-axis, so you can also see it on the graph itself. So the y-intercept should be straightforward. You can just grab it off the graph or the table. It shouldn't end up as some weird fraction. My God, did I put -4 there? Crazy. And again, also, it is just the c portion. Because if you were to do this algebraically, you go 0 squared minus 6 times 0 plus 4, and the only piece that would remain is the c of your quadratic. So you could always just write this as 0 comma whatever the heck our c is. So lots of different ways to get the y-intercept. This question's usually only a point on the test because it's super straightforward, super easy. Now x-intercept. Our x-intercepts we can see on our graph. It's when we cross the x-axis. But we can see they don't happen at perfect, nice, whole numbers, and we can also see that in our table. We never got 0 out, right? If that existed, it would have happened here. Oops, and not there. Ignore that crazy line. And here. Because 0 is somewhere between -1 and 4. So if there's a 0 somewhere, it's got to be here. This at least gives us a frame of reference for what our x-intercepts will be. Our x-intercept is somewhere between 0 and 1, somewhere between 0 and 1, and somewhere between 5 and 6, a little bit larger than 5, right? So we're sitting there going, okay, we know roughly where they are, but we don't have a way to get them, not even with the sweet table. So this is when you have to do the quadratic formula. Because what we're looking to do is solve this equation, 0 is equal to x squared minus 6x plus 4. Which is exactly how our quadratic formula works, right? 0 is equal to ax squared plus bx plus c. So then it's just a matter of, all right, well, I know a is 1, b is -6, and c is 4, and then just using our quadratic formula to figure this out. This is terrible looking. That's a -6. You guys get it. So I'm going to do that a little bit below. I'm going to get rid of this vertex information, and I'm going to go ahead and do our quadratic formula. So our quadratic formula, -b, so a -6, you can just write down +6, plus or minus the square root of -6 squared minus 4 times a times c, all over 2a. And this is, again, something you can do in your calculator. We could actually type all of this in, -6, plus, and we'll just do this, oh, I should have done this as one giant fraction, huh? -6 plus the square root of, I have to use parentheses around my -6, that's very important, otherwise it will tell me that that's -36, minus 4 times a 1 times a 4. And this is all over 2 times 1. And you do not need to be this silly about it. If you wanted to clean this up a little bit, make this 6 plus or minus 36 minus 16 over 2. You can do this, right? Getting you to 6 plus or minus the square root of 20 over 2. You could definitely clean it up a little bit by hand or just type it all at once in your calculator. Now, we see this thing somehow simplifies to root 5 over minus 3. So let's just, for the plus version of it, right? So let's just see how that would have happened. Why do we get this? Well, how? Sorry, I'm confusing myself. Did I put the plus version in there? I did. Oh, I typed in a -6 at the beginning. What a dork. What a dork. Let me fix this. It should have been a -6 up in the top, right? I tell I immediately knew something was wrong because I was doing this by hand at the same time. Thank goodness. But I also would have realized something was wrong because I have an idea of what these are. So if I had actually thought that it was going to be √5 minus 3, we'll see what that was, but I don't think it was going to work out well for me. So we have, the actual answer is √5 plus 3. How this happened was, if you wanted to know the math behind the simplification, this is 6 plus the square root of 20, which we can simplify to 2√5 all over 2. And 2 goes into both of those pieces. So we end up with a 3 and a √5. So that's exactly what the calculator did for us. It simplified the fraction and the radical at the same time, which is awesome. We know for this question, I'm going to want the approximate answer back out. So we can go ahead and just press the little squiggle line button, which those of you without the sweet calculator is just what it'll give you in the first place. This is 5.24, which is that value, right? So this looks good, makes sense. That's all right. For the minus version, we go ahead and bring back up what we had and just change in the numerator this piece to a minus. And we get, -√5 plus 3, which is approximately, so this is the plus version, the minus version is 0.077, which is this value, right? So we can actually use our graph, use all this to sort of double check that what we're getting out makes sense. Now, we should give our intercepts out as ordered pairs. So I'm going to erase some of the stuff I have here and rewrite them as ordered pairs. These two answers we just got. So once we use the quadratic formula, we found that our x-intercepts were negative, oh, not negative, my goodness. My goodness, thank God I had that graph there to keep me sane. 0.77, 0, and 5.24, 0. Just as to point out again, if I had accidentally not done that, had made my first mistake when I typed that in and got out this √5 minus 3, if I had used the little approximate button, it would have told me my answer was negative. And I know that that's not the case because that would put my x-intercept between 4 and 11 as an output, and that doesn't make sense. So use your graph to make sure your answers make sense. We do still have 4 more things or 5 more things. Not a lot of things I'm going to ask you about on the test, right? We know after the x and y intercepts, we could definitely have to identify the vertex, which we already did from the graph, from the table, and then we actually did it by hand too. Remember though, your vertex, don't just give me x equals 3, give me the point. We have our axis of symmetry. Our axis of symmetry is that line that divides our graph right in half. Boop, 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 boop. Right? And it has to be written as x is equal to, and then whatever that line was, which is 3. Remember, it will always match up with the x portion of our vertex because it is the line that cuts through our vertex. We may be asked, does this thing open up or down? Which again, we could actually look at the graph or just look at the fact that our A is positive to see this thing opens up. We may be asked, is the vertex a max or min? And again, if we look at the graph, this is straightforward. If we didn't have a graph, we would just quickly sketch an upward facing parabola and realize the bottom is the minimum. And then we have 2 more pieces, our domain and our range. Domain, what x values are we allowed to plug into this equation? Well, we can plug in anything we want, right? If I wanted to in this table, I could go up, I just want it to be on the table already. I can go up and down forever. Numbers start getting gigantic in terms of the outputs, but I can plug in negatives, I can plug in positives, there's no issues, I never get out error, which is when I'd have a domain restriction. I can also look at my graph. If I scan from left to right, I can see that I hit an arrow in either direction, so my domain for this thing is -infinity to infinity, all real numbers. And then our range, the possible x's, or not x's, y's. Same kind of idea, except for here, when we scroll around in our calculator, we can look at these y's and see what we get. And obviously I can get out bigger and bigger and bigger numbers, but I can't get any negative or many negative numbers. These are the only negative numbers I got out. And that's because if we did our scan from the bottom of our graph up, so we're scanning, 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 the first thing we see, oops, I meant to have my yellow. The first thing we see is the vertex, and then we go up and there's an arrow. So we can get out anything, but like we said, our vertex is a minimum. So our range starts at that minimum, which was -5, right? This is going to match the y portion, and then it'll go up forever to infinity. So from -5 up to infinity. Right, so that's all the bits and pieces that you're going to have to grab for graphing a quadratic. And yeah, that's it.